Welcome to Unit 8, Inference for Categorical Data, chi-squared. This is topic 8.4, Expected Counts in Two-Way Tables. So let's talk about what this video is all about. We will now start to explore how a chi-squared test can be used to test claims about the count of two categorical variables. Now, recall chi-squared goodness of fit test was only for one categorical variable at a time. And we wanted to see how well does the values we observed fit with what was expected. Well, this is very different because now we're working with two categorical variables. So there's two different types of tests when you're working with two categorical variables, a chi-squared test for homogeneity and a chi-squared test for independence. It can be kind of tough to differentiate between the two, but we will learn in topics 8.5 and 8.6 that the procedure for each of these tests is really essentially the same, but you do need to learn how to see the difference between the two of them. All right, so let's talk about why we need those expected counts. So both types of tests, homogeneity and independence, are chi-squared tests, right? So we're going to be using the same chi-squared test formula that we've seen in the past. This is the chi-squared test formula. Remember, chi-squared is a measurement of how far our observed values are from the expected values relative to the expected values. So you simply take the observed value minus the expected value for each category, square it, divided by the expected, and remember this means that we're going to sum them all up. That's what that Greek letter, it's a Greek capital letter sigma, but anyway, hopefully by now in some math class you have seen that that's the symbol for a sum. So we're just going to add them all together. So this formula does require the observed counts, which you will see in a two-way table. I mean, all these problems that we're going to talk about, you're going to be given a two-way table. So those are all your observed counts. What you need to do is find the expected counts. The expected counts will be needed to be calculated. And that's the whole purpose of this video. And this topic 8.4 is really how to find expected counts in a two-way table. And then when we move on to topic 8.5 and 8.6, we'll actually show you how to carry out the test, steps 1, 2, 3, and 4, all that fun stuff. But, you know, sometimes it can be a little bit tricky to find the expected counts. Hopefully by the end of this video, it's no longer tricky, but that's why they have a whole separate topic here, just that way we could go over this. All right, so let's, to truly understand this, listen, I'm not going to lie to you. I can show you a two-way table right now, and I can tell you how to find the expected counts in probably under a minute, but you won't know why. You won't know where those numbers are coming from. So as a good teacher, I feel it is important for me to actually explain where these expected numbers are come from, even though at the end, it's very, very easy to find them. Okay. So expected values are related to the null hypothesis. So in a test for homogeneity, we are trying to see if there's a significant evidence of a claim that there is a difference in the distribution of a categorical variable across populations or treatments in an experiment. So basically in a chi-squared test of homogeneity, we have different populations. One of the examples we saw was middle schoolers, high schoolers, and college students. And we wanted to see, across those three populations, is there a difference in the distribution of another categorical variable? And the example there we were using was social media platforms. We had Twitter, Facebook, Instagram. So is there a difference in the distribution of kids that use those different social media things across those different populations? I could sit here, in many different examples, right, that we could have with this. We could do eye color for Canadians versus Americans. So we got these two populations, Canadians and Americans, and we're looking at, is there a difference in the distribution of eye color across those different populations? So that's a chi-squared test for homogeneity. Homo means the same, right? So the chi-squared test is really seeing the knowledge that, they're all the same. The distributions are the same for each of the populations. Eye colors for Canadians, they're the same as eye colors for Americans. Social media preference for middle schools, oh my gosh, it's the exact same for high schoolers and college students. So that's why we're called a homogeneity test, because we're saying in the null that the distributions are all the same for each of the categories across the populations, okay? So that idea needs to be understood in terms of what the expected counts actually mean. In a test for independence, we are trying to see if there's a significant evidence of a claim that two categorical variables are associated with each other, which means one variable affects the other. So the example we're going to look at here is gender associated with political party preference? So does being a female make you more or less likely to be Democrat, Independent, or Republican? Same thing for male, okay? And really, I talked about that the actual procedure for these tests are pretty much the same. Really, the only difference comes when you actually write out the null and the alternative. You have to kind of know what kind of test it is. Now, I will give you a big hint here. An independence test is clearly asking you, is there an association? So if you're asked about an association between two variables, it's going to be independence. If you're asked about a distribution being the same versus different across populations, that's a test for homogeneity. So you do have to study that and kind of understand that concept. So the null hypothesis for homogeneity test is that there is no difference in the distributions across populations, and the null hypothesis for an independence test is that there is no association between the variables. So keep that in mind when it comes to finding the expected values. Okay, so this is it, right? The expected counts are based on the assumption that the null hypothesis is true. Remember, when you find those expected values, you have to assume that the null is true. And I'm going to explain that in more detail when we look at these examples. But once you understand that, we need the expected counts to show that there is no difference in the distribution of the categorical variable across populations, or that there is no association. So how could we actually calculate the expected counts to show no difference or show no association? It's actually quite easy. It's a very, very, very simple formula. So for every box in that two-way table, to find the expected counts, you take the row total of that box, the column total of that box, and you multiply those together, and you divide it by the table total. So again, I told you that I could explain how to find the expected counts in under 30 seconds. So there it is. Row total times column total divided by table total. But I want you guys to understand what these numbers are coming from. So let's take a look at this first example, which is a test for homogeneity. So here we collected data from 3 random samples of middle schoolers, high schoolers, and college students, and we asked them what was their preferred social media preference, Facebook, Instagram, or Twitter. So what we're going to say here is the null is that there's no difference. The 3 populations are all the same. It doesn't matter. So, these numbers are the observed. So you got to understand that all of these numbers here are the observed values. We saw 188 middle schoolers use Instagram. We saw 44 college students use Facebook. Those are all the observed values. What we're looking for now is the expected values, okay? And you got to understand it like this. So we have to understand, right, that the distribution should all be the same, meaning not equal, same proportion, right? Because the numbers are always different here. So let me explain this as best as I can. So you have to start with the totals. For example, 80 out of 570 people like Facebook. So I'm going to write that down here. 80 out of 570. 80 out of 570 is about 14%. So what we mean is the same across populations is this. If 14% of all kids, middle schoolers, high school, college, all people in my survey, 14% use Facebook, well then, if it's really no difference, then I should see 14% of middle schoolers use Facebook. I should see 14% of high schoolers use Facebook. I should see 14% of college students use Facebook. So that's where the formula actually comes from. So for example, we saw 12 middle schoolers use Facebook. What number should be there? Well, you take the column total, it doesn't matter the order, but the column total 80 times the row total 150 divided by the grand total 570. So I'm going to take that 80 out of 570, that was that 14% of people that use Facebook, and you multiply it by 150 middle schoolers to figure out how many middle schoolers should be using Facebook. So there's that formula, column total times row total divided by grand total. But it all starts with really the overall 80 out of 570. That's that 14%. So then when we move on to high schoolers, we should see, again, 80 out of 570, about 14% of the 200. So that's going to be 80 times 200 divided by 570. So this part right here is the 14% of people that use Facebook. And if it's truly the same across the populations, when I take that 14% and times it by 150, times it by 200, times it by 220, I will get what I expected in each of those values. And then I can move on to Instagram. So I have all the work kind of done for you here already. Well, at least started here for you. So again, I want you to really most at the end of the day, a lot of kids just remember, all I got to know is row total times column total divided by grand total. Yes, but I want you to understand why, because that's, the AP test is going to really test you over the why. So here again, we're looking at the fact that, again, the null is that there's no difference. So let's go back to Facebook, for example. 8, and I'm going to actually grab my calculator here so that way you can see me doing the calculations. Okay, so again, 80 divided by 570. So there's that roughly 14%. If you don't believe me, just hit it. But there's about the 14%. So I'm going to do 80 divided by 570. And then that's, again, I don't know why I just did it twice. That's at 14%. And I'm going to times that by 150 because what I'm saying is that, hey, if it's the same, I should see the 14% of middle schoolers using Facebook. So again, 21.05. So that's the number that goes right here, 21.05. That's the expected number. Saw 12, expected 21.05. And I literally have to repeat this process, and that's why there's a whole separate video for this, because this does take time, for every single one of these. So again, I'm going to repeat this for high schoolers, right? So once again, 80 divided by 570, there's that 14%. And I'm going to times that by the 200 high schoolers, and again, that is 28.07. And then I'm going to repeat it for college students. And again, 80 divided by 570, that's my 14%, times the 220 college students, about 30.88, if you round that to two decimals, 30.88. So again, now what we're doing is we're comparing the observed values to the expected values. So we see high schoolers were pretty close, but middle schoolers we observed way less. College students we observed way more. So again, is this going to lead us to evidence that they are not the same across the different populations? Now, once you get the hang of this and you get used to it, it does become pretty easy. So again, for middle schoolers to use Instagram. So I'm going to take the row total, 370, times the column total, 150. I'm sorry, I said that backwards. Column total, 370. I mean, obviously it doesn't matter the order, but 370 is the column total, 150 is the row total, divide that by 570. The key is that the 370 out of 570 is there because that's the proportion of all people use Instagram, and I'm multiplying that by 150 to figure out how many middle schoolers should be using it. So 97.37. So you literally have to repeat this process for every single one of these. So it is a little bit painstaking, but it is worth it to do. So that's how you find all of the values there. So not too bad, pretty simple, but again, it does take some time. So again, let's just do one more. Just want to make sure everybody's on the same page here. So college students who use Twitter. So that's going to be 120. That was the column total. Times the row total of 220 divided by 570. And I get 46.31. So 46.31. Sorry for my messy handwriting. So again, what you might notice there is that college kids that use Twitter is actually pretty close. The observed value was pretty close with the expected. So again, the whole point of this at the end is going to be saying, okay, we noticed that some are close, some are a little bit far off. Does all of this lead to evidence that the distributions are not the same across the populations? Or is there a lack of evidence? And basically, we're seeing numbers that are a little bit different just straight because of sampling. And again, that's what we're going to be learning in the next two topics, 8.4 and 8.5. All right, let's look at a chi-square test for independence here. Here is an example where we're looking at males and females, and we were asking them if they're Democrat or Republican or independent. And the question specifically says is, does the data taken from a random sample of people in a county show an association between gender and political party preference? So we measured a bunch of people in a particular county. Who knows, county in California maybe, and we saw males and females, Democrat, Republican, Independent, and we want to know, is there an association? So does being male make me more likely to be Democrat or Republican or Independent, or maybe there's no difference? So that's the key, right? You always start with the null. The null is that no, there's no association. Male, female, it doesn't matter. There's no association. Well, if there's no association, you start with your totals, right? So for example, Democrat. 372 Democrats out of 620. Okay, so 372 out of 620. I'm having calculator issues here. 372 out of 620 is 60%, right? So 60% of people, total people in this survey, were Democrat. So if there was truly no association, 60% of males, 60% of the 340 males should be Democrat. 60% of 280 females should be Democrat. And that's where we multiply, right? Because now we're going to take that proportion, 372 out of 620, 60%, we're going to multiply it by 340. So there's your formula, right? So right here, the Democrat males, that's what I observed, 176. The expected would be column times row divided by grand total, right? And again, it should all make sense. So I'm going to take 60%, I'm going to times that by 340, and there should be 204, I'm going to kind of squeeze in there, it's kind of hard. There should be 204 males that are Democrats. You're like, whoa, wait a minute, my observed value is way less. Let's look at the females. So once again, 60% would be of 280. So 60% of 280 should be 168. So you're like, oh, well, the females there's more Democrat females than what we expected. But it all goes back to that null. The null is that there's no association. It doesn't matter if you're male or female. You know, being a male doesn't make me more likely to be this or less likely to be that. It's all the same. So again, to calculate the expected values based on that null, you start with the total. You say, all right, listen, 60% of total people are Democrat. If that's true, then I should see the same across males and females. So again, here's another chart. You know, this is what you want to do on your test, right? If you have a quiz or a test or a homework assignment, you have to set all this up. You got to kind of make a nice little chart here. So this chart up here, this is the first chart. This is going to be given to you. Those are your observed values. You just now have to find all the expecteds. So let's see here. We already did the Democrat males. We said 204 was expected and 168 females. Again, that would be keeping the 60% across the board, showing that it doesn't matter if you're male or female, 60% chance to be Democrat. And then we got to do Republicans, so it'd be 173 divided by 620. That's about 28%, a little bit less, but about 28%. So let's actually do the math with this, right? So we take the 173, divide by the 620, and again, there's that just below 28%, and I'm going to times that by the 340 males. Because again, think about what I'm saying. If 28% of people are Republican, and there's no association, 28% of males should be Republican. So again, 94.87. And you say, well, wait a minute, can I have decimals? Yeah, decimals are totally okay here because these are means in the long run. These are expected values. Expected values are allowed to be decimals. And the same thing with the females. Now again, you could do the total first, then multiply by the total males and females, or you could follow the formula. So let's just do the 173 is the column. 173 times the row, 280, divided by 620. So this is really the same thing. So the 173 out of 620, that's the 28-ish% of people that are Republicans, and then I'm timesing it by the 280 to get the females. That should be 78.13. Now, the only thing I got to be very careful of here is showing you that you don't want to do, I'll get kids that will do the wrong order. They'll do 173 divided by 620, then they'll times that by 280. That's not going to follow order of operations. Oh, wow. Never mind. It did. I'm so sorry. It did work because it did the dividing and then multiplying. So, yeah, it wouldn't matter. Okay. Sorry about that. Yeah, so it's good. You could do that. But again, following the formula, it's row total times column total divided by grand total. All right, let's move on to independent. So again, 75 out of 620. And I typed that wrong. 75 out of 620 are independent. Again, that's about 12%. So again, think what I'm saying here. If 12% of people are independent, 12% of males should be, 12% of females should be, because that would show that the null is true and that there is no association. And then again, so now if I want to do this a little bit faster, I could do this 75 times 340 divided by 620. So that should put 41.13 males that should be independent. And then you look at that number and you're like, what? There were only 11. That number's way off. And again, that's all signs pointing to maybe there is an association. But again, that's why you actually got to finish the test up. So 75 times 280 divided by 620 is 33.87 for the females. Okay, so moving forward, what are we going to do next? We're going to find those chi-squared numbers for each one of these categories, and then we're going to put it all together to get a p-value. But again, I'm not asking, I don't want to suggest that you should make a conclusion based on this alone, but, sometimes it's worth just thinking about. So, like, if you just look at the numbers, like, for example, look how many less males are Republican than expected than what actually was. So there's 153 observed male Republicans, but we only expected 94. You're like, oh boy, that's a big difference. Same thing with the Democrat females, right? We observed 196, we only expected 168. So you start to get the sense of, wow, these numbers aren't just a little bit off, they're kind of a lot off, especially with independent. And then you start to wonder, Well, maybe females are more likely to be Democrat. Maybe males are more likely to Republican. And then again, that's what's going to feed us into making our final conclusion. But we can't just have it, can't just do it based on, thoughts and feelings. We actually have to crunch the numbers to get a p-value to make the accurate conclusion here. So at the end of the day, please make sure that you understand to get the expected counts in a two-way table. It's a pretty easy formula. Row total times column total, order of that doesn't really matter. Row total times column total times row total, then divide by the grand total. But you got to understand why you're doing that. What are those numbers producing? They're producing numbers that show no difference, show no association. Okay? And it's all proportion based, right? I'll get kids that say, I should see the same numbers. That's what it means, the same. I should see the same number of males and females. Well, no, you can't say that because there's more males than females. So they don't have to be the same number, but they do have to be the same proportion. That's why it's important to start off with the 372 out of 620. That's that 60% that are Democrat. Then we could say for them to be the same, it should be 204 for the females, or for the males, 168 for the females. So yes, those are different numbers, but they're the same proportion when you actually start dividing by the totals. That's important to understand. All right, guys. So the difference between a test for homogeneity and a test for independence typically comes down to how the question's worded. So that's the other takeaway from this video is you really got to understand that there are two different types of tests, and it really all comes down to what are you being asked? Are you being asked about 2 or 3 populations being different across a variable, or are you being asked about there being an association or not? Independence tests are so easy to recognize because the wording literally says, is there an association? If you're asked, is there an association? Trust me, it's a test for independence. All right, so moving forward, the next video, we're going to really tackle how to go through steps 1 and 2, setting up the chi-square test. But, really understand that getting these expected counts down pat is honestly the hardest part. Once you get that down pat, once you find all of your expected values, then you just have to do the math work to get everything else done. So we'll talk a little bit more, and we'll actually use these exact same examples in the next video. That way there's some consistency there, and we'll be ready to go. All right, guys, good luck.